Hello, Borden.
Hello.
Hey. How many exams do you have?
I have 5.
So is all of the exams take home? How does it work in other courses?
3 or yeah, 3 of them are take home and then 2 are in person.
Oh, in person, you mean?
Or like live. So I have 2 hours to do them.
Okay. So it is timed, you mean?
Yeah. So like a normal final.
Oh, 2 minutes. Hello, Curtis.
Hello.
Let's see. So there was a homework due today. Presumably that went well. And there's 2 things, right? There's the final exam remaining. The final exam. I intend to will be uploaded this weekend. And probably even today, not sure. I wouldn't want to promise that. And it will be due on December 11th, which is Friday. And one more thing, there's a course evaluation on D2L. So it's good to have evaluation if you want to. Should take only 5-10 minutes, I suppose. That's all. Is there anything else you think I should point out?
I just had a quick question.
Yes, Borden?
I just realized I didn't turn in the most recent homework. Can I just email it to you right now?
Sure. Yeah, this is the last homework, and I think you have submitted almost every homework on time. So yes, do that. Yeah.
Okay, thank you.
Yeah. Okay, so we want to do a last example today in using conservation principles. So remember, one of the conservation principle we used is let's give a name of this. So we stress on a charged sphere. That's what we want to calculate. By stress, I mean just a pressure. The idea is that if you have a sphere of radius r, and let's say it's uniformly charged. Right, and yeah, and we would like to, and we know the electric field due to this, right? It's clear what the electric field is. So that's your electric field. In fact, there is electric field inside also, right? It's all everywhere there, but it doesn't grow linearly inside. Outside it decays off as 1 over r square. Inside it increases. So the electric field is everywhere as a function of r, vector r. That's equal to, if you're inside, it is q over 4 pi epsilon naught. And it grows linearly. If you're right at the center, the electric field is 0, and it grows linearly. So if you put in the vector r nature also, that's r over r cube. So notice this is linear because there is a magnitude r on the numerator, and denominator is just the radius of the sphere. So it increases linearly from center to the surface. And this is for r less than epsilon, that's inside. And if you're outside, it decays off. That's a familiar thing we know. So it's vector r over r cube. So the only difference here is that one is the radius of the sphere and one is the distance of observation. So this is when you're outside. Okay. And given that electric field, we can ask the question, if this is the only sphere that is sitting in the universe, then all these charges would like to burst out, right? They all want to stay as far away as possible. So there is a tendency to get separated away from each other, and that leads to a pressure on this ball, and pressure is equal in all directions. So this is electric field, so there's a pressure in all directions, and we would like to know what that pressure is. That's what we want to find out. And for that purpose, we use the conservation of momentum equation. That's a stress tensor, that's a momentum density, and that is a force density. What are these quantities equal to? First, let me write the flux of momentum, or the stress tensor, is equal to, so that's it is given in terms of the energy density U times the unit dyadic minus a dyadic relation. This is not a dot product. This is an outer product if you want. So it's H times B. I should clarify what is H and U here. So U is the energy density. That's 1/2 of E dotted with D plus 1/2 H dotted with B. And what else is there? That's U. So G is D cross B. And for this configuration, there is no magnetic field, right? So magnetic field is 0. I can add to that feature. So that's magnetic field is equal to 0. So that's immediately 0. There's also this simplification that this goes away, and U is nothing but, that is D is epsilon naught, remember. So that's 1 over 2 epsilon naught E squared. So when you take the dot product, that's just simply 1 by 2 E squared in this scenario. And since again here it is in the radial direction, this will be equal to 1 by, so that is U itself, that is 1, and this is minus epsilon naught E squared, and R hat times R hat, right? Because E is, electric field is always in the R hat direction, so I can write that. So that's 2 times U here, right? So this is also equal to U times 1 minus of 2 times U, the R hat. That's just collecting some information if you want. So, so again, in our problem, T is equal to U times 1 minus 2 times U times R hat. A standard relation is that if I were to take the trace of this, the trace is, remember, if you think of this as a matrix, sum this up, so that's a factor of 3. When I take the dot product, that's 1. So trace of T actually is equal to 1, just U. Right? That's just U, so it is 1 times 2. So that's a nice relation, and U itself is half epsilon E squared. So that means inside it will be some quantity and outside it will be some quantity. So with this information, let's proceed to work out what this force is. So how do we calculate this force? So let's go back. Actually, let me draw that again here. So that's your sphere, uniformly charged, and let's consider a volume right above the surface of the sphere. Remember, the radius of the sphere is R. So right a little tiny bit above the surface, I consider a volume V, and I integrate this momentum equation with that volume. So since first term is anyway 0, so what I have is integral p cube r, this volume of the divergence of T plus F, or actually I want to do one step before that. Before actually I do the integral, I want to do one thing. So first I want to take the dot product with respect to R hat. And that's because this is a vector force density. I would first like to take the dot product with R hat. That's the idea, is that these are all radial forces. If I were to actually integrate it out, because these are vectors, they will all cancel out. Like for every vector on this side, that would be a vector on that side. So vectorially, that cancels out, but that doesn't mean that the pressure doesn't exist. So to get rid of that feature, I will multiply by R hat, and that's equal to 0. And then I integrate over the volume. So that way I'm taking a scalar relation, and that can contribute. And we want to calculate. So this is what we will define as a force on the sphere. This has the dimensions of force because this is force density. Density cancels, so there's a total force there. And then we will divide it by the area to get the pressure. So let's define this to be the force. Whatever this comes out, we will define this to be a force. And we will see that divided by the area will come out to be the pressure. So F is equal to minus of, this is a, we can use divergence theorem here, but it is not yet a divergence theorem because this has to act on both R, right? So I'll manipulate this a little. So this is V, EQR. I want to act on both. Let's divergence charted with hat. So that's not completely the same as this. So I have an additional term. So I subtract that out. So when I subtract that out, that's just positive, right? So earlier it was negative. Subtracting means it's positive. So it's EQR. And I operate that on, so this gradient now has to operate on R hat. But at the same time, I have to stick to this T notation, right? So what I'll do is that, so this is Tij. I go to index notation, and then I say this was del I. That has to go with T, but it is acting on R hat. But R hat is nothing but vector R over the magnitude of R, and that's J. That's the relation. I can use divergence theorem here. We will evaluate this separately. I can use divergence theorem here to begin with. So divergence theorem now gives me, this is evaluated on a surface.
Suggestion, you need to lower the camera.
Oh, sorry, thank you. Thanks for putting out. Yeah. Okay. I hope this was readable, right? This equation that I was writing.
Yeah, it was just the new line you were writing.
Okay, good. Okay. So I wrote this down. Now I want to express or evaluate this. I can use the divergence theorem to evaluate that. This is R hat dotted with T dotted with R hat. Right? Notice there's a dyadic, so I can take the dot product from both sides. Right? And this is the R hat because this is the normal to the surface, and this R hat because I multiply R hat from the right hand side. This is evaluated on the surface of the sphere, that is right at on the edge of this. And the second term here, remember the gradient of R hat is, so let me do that here separately for a moment. So this is vector R over R. This is, yeah, I can hit the numerator. That gives me vector R divided by R. Or I can hit the denominator, which gives me minus 1 over R square. This is vector R. This stays as it is. And I can gradient divided by R square. But that's just 1. The first term is just 1. The unit dyadic one, and the second term is R times R hat. I can write that as vector R over R cube, which is R hat over R cube. So if I use that in this relation, this multiplied by this gives you a trace. So this is plus E cube R. This is a surface integral. This is a volume integral. T multiplied by this, that is an overall 1. You divide that by R here. And this is trace of T. Trace of T, because T multiplied by 1 is equivalent to trace. And this is R hat. R hat on both sides. 1 goes with the left, 1 goes to the right. So that's minus of R hat dotted with T. R hat. So that's our expression for the force. So let me rewrite that in the next board so that we have that. So we have an expression now. Now we have to actually evaluate that for the sphere. That's all that is remaining. Okay. Shall I move the board?
I'm good.
Yeah. Okay. So let me move that board and let me know if you want to. Okay. So the force is again rewriting that expression. There is a surface integral of dA times r hat with T r hat, and there is a volume integral. Oh, there's a minus sign there, right? So the minus sign here, front, plus there is a volume integral d cube r on the sphere, inside of the sphere basically. And this is trace of t, which we figured out before, minus of r hat dotted with t dotted with r hat divided by r. So let's see what these quantities are. We already know some of them. So trace of t, recall, is it's at u times 1 minus 2 times u times r hat. So what is r hat dotted with t dotted with r hat? That's equal to, multiply on both sides. 1 gets multiplied by r hat on the left and from the right. So that's just simply u, right? The first term. And the second term, again, r hat gets multiplied by r hat from left and right. So this is minus 2u. So that's equal to minus u, where u itself we will write in a minute what that is equal to. So that's surface integral of u. And here there is a trace of t, and so trace of t, remember, was, let me write that down here. Trace of t, we showed that was equal to u. So trace of t minus of r hat dotted with t r hat is equal to u minus of minus u. That's equal to 2 times u. Okay, so the force then, this is not a vector, sorry, this is a scalar. So the force, the magnitude of all the forces on the surface is equal to the surface integral of the energy density plus the volume integral of 2 times the energy density. So let me say plus 2 times the volume integral of the energy density. And energy density itself is half, we said it was half epsilon e squared. So what is that for the sphere? We are interested only in the inside. Either we are doing the inside of the sphere volume or right on the surface, which is, so it is sufficient to say what is the electric field inside the sphere. So U is equal to 1/2 epsilon naught. Electric field inside the sphere is Q over 4 pi epsilon naught. And that is vector R, so it's a magnitude, so it is vector R over R cube squared. That's what it is. One of the epsilon cancels out, so this is inside the sphere. So that's equal to, one of the epsilon cancels out. We have 1 over 8 pi, and that is Q squared over 4 pi epsilon naught, and that is the vector radius r squared over r raised to 6. should have the dimensions of energy, which is 1 over r, q over r if you want. And then there's an additional r cube. So there's a q square and there's a 1 over r raised to 4. It's 3 from the volume and 1 from the potential. So that's looks dimensionally correct. Okay. So what is this equal to? Let's do these two integrals. So first let me do the surface integral. That's an easier one. So surface integral will be dA of u. You just evaluate it right on the surface. So I just have to replace that r with a capital R itself. So that's surface area, that's 4 pi r square. That's the area dA. And I multiply that with the volume on that surface. So that's 1 over 8 pi times q square over 4 pi epsilon naught times r square. No, I don't put it. Small r should be capital R. So that's capital R square over r raised to 6. Okay. So all that boils down to 4 pi and 8 pi gives you a factor of half. And this is 1 over 4 pi epsilon naught. And all the factors of r cancels out, and there's a q square over r square. It's pretty much if there were two charges, 2-point charges q, it's a force, and then there's a factor of half, right? It looks very familiar expression, but this is just the first term. Correct? And did I miss a sign here by any chance? Oh. U was so much. Let me make sure I'm doing this all okay. R hat. Yeah, so this was R hat. Yeah, this should be plus, right? So there's a small mistake here. So that is, this was minus. When I substitute this in there, there's already a minus sign. So that becomes a plus, right? This is a plus. So to check this out, I changed the sign here. And this was a 2 times u in here, right? So there's a trace of t. This was 2 times u, which was with a positive sign. So that stays positive. Okay. Better, correct? Okay. So that's your first term. So now next I have to do the second term. Almost there. Very similar exercise. It's just now that we have to do a volume integral. There's a 2 factor of 2 there, so I'll keep the factor of 2. So I just have to add the resulting 2 terms. So that's on the volume V, d cube r times u. And since I'm inside the volume V, I can still use the expression that we calculated for inside the sphere. So that's 2. There is no angular integral, so that gives me just 4 pi. There's an angular d theta and d phi, that just gives you a 4 pi. And the radial integral is 0 to capital R, r square dr. And the expression for u, which is right here we have. That's r square over r raised to 6. And we have, oh, I again messed up, right? Sorry, I think I was wanting to take care of that, but I messed up. Okay, go back to the expression here. Small mistake here. Trace t minus r, I calculated it to be 2u, but there is a 1 over r there, so I shouldn't forget that. So this is 1 over r. So the same expression, I made two mistakes. This was a minus sign before I changed the sign to plus, and I forgot this 1 over r there. So there's a factor of r, so I could copy that down there. Right. So this is now when I'm evaluating this is u over r that I'm supposed to evaluate. So there is an extra 1 over r. Otherwise, dimensionally, I will be off. So let's get the correct number of r's. So 8 pi and 8 pi cancels out. So 4 pi into 2. This is 8 pi. So that goes away. So that gives me whatever is remaining is q square over 4 pi epsilon naught and 1 over r raised to 6 and 0 to r, as in 4 r's in the numerator, 1 in the denominator. So that's r cubed dr, which is r raised to 4 over 4. This is equal to, so let me do that here. This is 1 over 4 times 1 over 4 pi epsilon naught, and this is q square over r square. So that r's all cancel. If I add these two quantities, I get the force, and which then can be used to calculate the pressure. So the force will be add these two quantities. It's very straightforward. So it's 1 over 2 plus 1 over 4. And it is 1 over 4 pi epsilon naught and q square over r square, which is exactly 3 over 4. Usually, this is done for a conducting sphere, and then this factor, the only difference is that this factor changes. So what we have actually done is that we have a solid sphere. We didn't say it is a conducting sphere. A solid sphere experiences a pressure because each of these charges want to separate out. So if you talk about the pressure here, the repulsive pressure, that will be force per unit area. So we calculated the magnitude of all these forces. So pressure P, the force per unit area, and we can divide this out by 4 pi r square. So this will be 3 by 8 pi 1 over 4 pi epsilon naught and q square over r raised to 4. That's the stress it experiences. Again, the only difference that comes if you were to actually do this for a conducting sphere, the difference will be that conducting sphere, all the charges will be right on the surface. There will be no volume integral necessary. So all the volume terms will go away, and the second term will not contribute, and this will instead become 1 by 2 instead of, or it will be just 1 by 4 pi instead of the factor of 3 by 4 showing up. So this is, again, realize that this will not be an easy calculation to make simply using statics alone, because one wouldn't know how to find this forces between these two. They are so close, they will be divergent quantities. So one finds the stress in this manner, and it comes out to be a nice, simple expression. And with this, I'll stop. It's a little early, but I think it's the last class, so I won't do anything more. That's all. Thank you, and thanks for listening.
All right. Have a good winter break.
Same thing. Foden, enjoy. Let me know how it goes. Yeah.
Sounds
Bye.
good.
Uh,
Thank you.
Happy New Year and happy Christmas. Merry Christmas.
Yeah, you too.
Mhm.